Okay, hello everyone. Welcome to another episode of the Holotube. We're very happy to have Nick Poovuttikul today from Durham University, who will be talking about global symmetries and G2 group and holography. I don't remember the title exactly, sorry. But I'm sure it's going to be very interesting. So as usual, just please everybody ask questions whenever you want, just unmute yourselves and I will only intervene if time is of the essence. So please, Nick, go ahead. Thanks a lot.
Okay, thank you. Thank you so much for having me here. And yeah, well, it's a great pleasure to talk in Holotube. So I will be talking about this stuff, which the meaning of them hopefully will become clear to you in a bit. So this is a work I did together with Nabil Iqbal from Durham, who is in the audience. So please feel free to ask him difficult questions. That was a joke. So please feel free to ask me any questions. There is no stupid questions, only stupid answer and stupid joke. Okay, so before we get to the meat of this, let me get the overall kind of like overarching motivation for the whole talk. So for those of us who study quantum field theory, like one quantity that we would like to have, is the partition function, which essentially contains pretty much all the information in your theory. But for strong interaction, this is quite difficult to compute for most of the time. So there are simple cases, like when you have the strong weak duality that you can express it in a simple form, like in the holographic dual, which I doubt I have to explain to this audience here. But if I have to, then please let me know. I will just skip it for now. The other way, which is kind of go hand in hand with this thing, is to look at the IR sector of the theory, and then you build an effective field theory of that, which is, that this is a fancy way of saying that you guess what is the partition function using the global symmetry of your system. And today I will talk about one of such EFT, which is hydrodynamics. So now, what do I mean by hydrodynamic when I say hydrodynamics or hydrodynamic limits? So let's imagine that you put a theory on a circle. On the finite temperature, not the circle, on the cylinder, and on the finite equivalently by the finite temperature. And then you start checking it, and then you look at how the operators evolve. And if there is a big window where you have all the operator decays much faster than the one that is a conserved current, then this is the window that there's these time scale are the one where hydrodynamic behaviors will kick in. We also assume that there is no branch cuts at small omega and k at these time scale of your interest, so that you can assume that these quantity can be created and expand, and the solution will always be exponential in time, like this, not the power law. Okay, so what does this mean? So if this limit can actually be achieved, then it means that if you have different theories, but with the same global symmetry, then they can describe by the same equations, essentially, because the microscopic stuff described by all these like other operators it's already decayed away. And this is kind of intimately linked to the bosonic sector of the theory that described by bosonic sector of holographic theory, that described by like S-Hilbert action plus bunches of gauge field that corresponding to the global symmetry of the boundary theory. And just to make sure that we are on the same page, let me introduce some notation. So this is what the hydrodynamic looks like in what I used to. So you write down a partition function. Let's say it's a functional metric and some gauge field A, let's say U1, and if it's invariant under the diffeomorphism and the gauge transformation, you have a conservation of number and conservation of T mu nu. So hydrodynamic is essentially amount to expressing these conserved quantities in terms of some proxy, which is the conjugate of the conserved current, like T is the conjugate of, or 1/T is a conjugate of energy, U is conjugate of momentum, and mu is a conjugate of the density, and then the background field. Then you do the gradient expansion. So there will be, write down every term you can possibly do at each order in derivative. For example, the zero derivative, these are all the terms that you can write. These are all the rank 2 symmetric tensors. And this is a vector, and then you go order by order in gradient expansion. So the only input here is, well, essentially global symmetry. And you have a macroscopic constraint, and then you assume that the gradient expansion actually exists, so that you can go from one derivative to higher order. And this is well, as we all know, this is a pretty simple equation and surprisingly reliable in strongly interacting system. However, in QFT, fortunately we have a lot more interesting symmetry structures. So you can have the ordinary symmetry, where you have the partition function is a function of background gauge field invariant under this kind of transformation. You can have something called the anomaly. This is what happened when you do this gauge transformation in the background field. You not quite get the same partition function, but it's off by some phase. It could be U1 or Cn. And you can also have a one-form symmetry. This is in the case where your theory has a line operators like Wilson line, 12 line, or like other defect, that one-dimension defect operators. Now you can have stuff like branes or surface operators, or those domain walls or those kind of stuff. And what you have to do here is your partition function will depend on like these higher form gauge field, which basically contain the high index. So this background field will couple to the current, like the ordinary one will couple to the vector current, which we saw earlier. And the integration of this thing will count the number of like point particle that you have in your system. For this one, for the one-form symmetry, you have the two-form gauge field. It's coupled to the two-form current when you integrate over the codimension 2 surface. Codimension 1 surface. Sorry, codimension 2 surface of the theory. Then you get the number of kind of like flux that pass through this system. Okay, but this is apparently not everything in the story. You can have a more interesting stuff, like you can have a product of the ordinary and the higher form symmetry, or you can use one to extend another, making like anomaly of these two. And you can also have like even crazier stuff that is not obeying a group axioms. So for example, for those of you who know about the fusion categories in topological field theory, or 6J symbols and those kind of stuff. So there are plethora of symmetries that are richer than just translation and the concept chart in your system. So, and that brings me to the dream of when we start this project. So there is ordinary symmetry, higher form symmetry, and then there is something called higher group global symmetry exists, which is like it's something that kind of like in the borderline of this type of symmetries. So it exists in quantum theory, and we can do it for ordinary. We can do hydrodynamic for ordinary symmetry. So how can we not do it for this higher group structure? It's more intricate symmetry structure, but it exists. So can you build a hydrodynamic version of that? And is it have a like observable and universal prediction in the same way as usual hydrodynamic does?
Nick.
And yes.
Can I just ask, since one can?
Yes, George. Is that Giorgio?
Yes. There are theorems that, at least in sort of microscopic quantum field theory, these high forms can only be an effective theory. They cannot be fundamental, like the Weinberg-Witten theorem and things like that. I mean, already at spin 1 you need a conserved charge. At spin 2 it only couples to gravity. It can only be something like gravity. At higher order it can only be composite particles. So why should this dream be true?
Okay.
If most higher form symmetries are effective theories, hydro is an effective theory. So you're building an effective theory of an effective theory. You see what I mean?
I see what you mean. Yeah. So okay. So let me get to. Okay. Let me make one distinction first. So I think you mentioned the something along the line of the like Coleman-Mandula theorem, like the higher spin object. So I'm not talking about higher spin. This is like about higher form. So this is essentially it just like the symmetry that does the job of counting the line operators. Now you can say, okay, well, are these symmetry like a fundamental symmetry, or are they emergent? So we can say, is QED a fundamental theory? like quantum electrodynamics. So these, well, we know that QED is not UV complete, right? You have a, well, you have a Landau pole in the UV, and in the IR you have a conservation of magnetic flux. So what I'm using here, what I will be using in a bit, is the conservation of magnetic flux, which it is true that this is a, it's not the, it will be going away somewhere because QED break down at the Landau pole scale. But it's, I guess to answer your question, this is like, it's the different regime of effective theory. So the symmetry may emerge in the scale like before the hydrodynamic kick in. So that would be the case in QED, in quantum electrodynamic, for example. Does that answer your question properly?
Yeah, thanks.
Okay, thank you. Any other questions, by the way, about? Okay, then I will just go ahead. Yeah, okay, so what is the holographic duo has to do with these things? So at least for us, like this is like a guide and a testing ground to that we, whatever these hydrodynamic theory that we cook up is actually correct, and we can try to derive one from another. Also, there's some people who are interested in, like a 6D SCFT or a 5D theory that has this higher group symmetry. So maybe this could be a template for them, but I don't think there are any of those in this audience. Okay, so now that was a dream, and here is the plan. So the plan is, okay, I will tell you what is a, simple example of QFT with the one form U1 symmetry, and how you make a two-group global symmetry that builds out of the zero form U1 and the one form U1. By zero form, I mean like the ordinary symmetry, and the one form is the one that corresponds to the line operators. And then I will tell you how do we build the, like sort of a cartoon version of how we build the hydrodynamic for the two-group global symmetry, and then a minimalist version of a holographic model that corresponds to these hydrodynamics. All right, so there is an example that we just talked about, like a four-dimension theory with the one form U1 in QED4. So when we look at the Maxwell theory, we can ask what is the global symmetry of the Maxwell? And well, okay, there's no gauge symmetry, and let's say forget about translation and rotation. So what the symmetry of the system is actually the conserved electric flux and the conserved magnetic flux, and this is I denote by U1E and U1M. So it basically just saying that there's magnetic flux which is conserved, which is without QED or without doing quantum, this would be something that you would have guessed. And these associated to the Wilson line and Topf line. So, and now let's say you couple this thing to like a trivial, some simple charge method that basically does the screen electric field away. So electric flux line can now gain an electric charge and it's no longer conserved. So what you have left, the right-hand side of this equation is no longer zero, and you throw it away from the effective description. It's no longer conserved. But if you don't have a monopole, like in this universe, then you can have a conserved magnetic flux, which is still a good description, a good symmetry to describe your Hilbert space in the IR or your field theory. So the partition function that is suitable to this DFT is this. Is a function, partition function depends on, okay, perhaps background metric and also the two-form gauge field, which is invariant under B equals to B plus D lambda, where this lambda is the one-form gauge field transformation parameter. And you couple them to the background stress energy tensor and the background, sorry, you couple this source to the current in this manner. Okay, so you may want to think about this in terms of gauging. Let's say you have a U1 symmetry and you want to couple them to some Maxwell theory, and then, kind of like taking these two systems separately. Like you have a U1, usual U1 fluid that, we talk about kind of like here, and then just gauging that. Now that there is that there's nothing wrong with that, you can do it perfectly fine. But I would say that it's not quite efficient way to do it. So first of all, when we look at the Maxwell equation, by doing that, then the Maxwell equation, it's kind of break the gradient expansion, right? You have like B star F, which is a second order in derivative, and equal. It's supposed to be equal, proportional to the the JU1 that coming from this partition function, and this is a zero order derivative. So you have to, do some acrobatic of rearranging the gradient expansion, which you can do, but it seems it is quite painful to do that systematically, and it has only been done quite recently by Pablo Cofton and Juan Hernandez recently. So also, if you were to do it classically, like no quantum, no averaging, then throw away this integral, then what you're seeing here is that you factorize like the fluid sector and the macro sector together. So this is justified, let's say, if you have a pressure that is like depending on only purely from the fluid parameter and the one that depends on the magnetic flux density. But if you don't have those, then it's a bit weird to do it this way. Also, relying on the gauge symmetry is a bit on the symmetry that got gauged away already. It's a bit weird. It's not the real symmetry of the system, and or put it more precisely, your Hilbert space doesn't know about gauge symmetry. So why would you use that to build an effective description? Also, like just another remark that we wouldn't do this the same game if to build like SUN color fluid and then you couple it to a gluon and then gauging it away again. Like, I mean, this would be like quite useless thing to do. And we know that we don't have to do that because, well, for SUN, like let's say SUN Yang-Mills theory, we know that there is a CN one form global symmetry, which is a discrete symmetry. There's no other global symmetry except translation and rotation, which is why we can just write down the concept T mu nu and nothing else. And this is the one that Polycastro-Son and Starnet did like 20 years ago. Okay, so now we go to the interesting example of two group in QED. And now this is just, it's kind of like the same QED, but the matter sector is a bit more complicated. So let's imagine the matter sector, but before you gauging, I just advocating against gauging, but let's to orient ourselves, let's try to do the gauging picture anyway. So you have a system, with two U1 with two conserved current J, and they couple to the two background view A1 and A2, and there is a mixed anomaly between them. So mixed anomaly meaning that the right hand side, one of them is a function of the field strength of the two U1, and you can add the counter term and move them around. Okay, so this is a system. This looks anomalous. So if you have this mixed anomaly, then you can gauge one of the U1 away. And by doing that, well, okay, this condition would be gauge will be zero off shell and will be gone. You have a conserved magnetic flux, and then the right hand side of this equation, the second line, will become the following. So it will become a function of an operator and a source, and a mix between the source. So I would say that I would claim that this theory is no longer anomalous, and the reason why is that, well, the right hand side is not a function of your source anymore. So this is like one clear description you can create, and similarly you can say that, well, that there's you can make this theory gap by saying, oh, okay, maybe that argument should come later, but okay, just the simplest one is that, well, if for it to be anomaly, right hand side has to be a source, and now it's not. So now we can try asking, okay, if we have like these two current, how can we get this Y identity from the generating function? And the way you can do that is saying that, okay, you write a position function in this way, and you demand that it is invariant under the following transformations. So you shift A by d lambda, where lambda is a scalar. You shift B by the big lambda, which is a one form, but you also add another piece, which is the some integer kappa multiplied by this parameter lambda, and then the flux. So this is what this is. It's also extremely oversimplified, and I think anyone who worked on two group before will probably get angry with me for saying this. But you can take this as a something that is called two group. It's the one where partition global symmetry. It's the one where you have this partition function and you transform it this way. I see Blaze open the camera.
Yeah, hi Nick. I didn't quite catch what's your definition for capital J in terms of J1 and J2. Yeah, J1 and J2, and now you have capital J.
Okay, sorry. Then the capital J is just, in this case, it's just the star of capital J is a star dA. It's the magnetic flux of the one that you want that gauge out.
Okay. Thanks.
Thank you. Okay, so where were we? Okay, so I should mention that this is like not the only symmetry system that has a global symmetry. Like this is the one that you got from gauging, but you should think of this thing as like a genuine global symmetry. This is as good as the other global symmetry that we can have. So we want to take this, and there are many other systems where you can actually get it without gauging, like in some QCD, QED-ish type model, in CPN type model, in 6D theory, and also in topological field theory. You have bunches of these guys. So another way that you might want to visualize and why that there is no anomaly is the following example. So this is the system that also has like a two group is the one we had before, but maybe bit more pictures. And the equation is that the ensemble of the ubiquitous vortex with the fermion zero mode living inside. So let's imagine like we have the previous system. We Higgs the gauge field, and you lock the magnetic field on the ubiquitous vortex. And on the vortex itself, you can look at this equation, these relations, like and compactify on a T2, for example, and it looks like it is anomalous, and that there is you can follow computation in Jackie and Rabi computations like 30-40 years ago, and you see that there is a zero mode living inside this vortex. But the whole system itself is not anomalous, right? Because well, I can, if it is really an anomaly, I cannot remove the zero mode. But I can, in this case, I can just turn off the magnetic field and it will be gone. And another reason why this is not an anomalous system after you gauging is that like there can be a bulb that make an inflow to the string, and the whole anomaly of the whole system is cancelled out, and the system is anomaly free. But this picture is quite intuitive in several ways. That we know that there is a zero mode living inside this vortex when you turn on density. So, and it should have effect. It could have effect, and you will see that it will affect the macroscopic transport of the system. I can try to say a few more words about the two groups. That is still extremely oversimplified, but with more details. So let's look at the partition function where with these following transformations. Now, what you will notice is that if I want to define a field strength for A, I can do it in a normal way. But if I want to define a field strength for this B field, like the one that's kind of like the covariant derivative, exterior derivative of B, then I would kind of fail because this annoying extra piece. So this means that the physical flux that you can define is this H, field strength H, which is the B, and you minus subtracted by the Chern-Simon terms, or the Chern-Simon tree forms. This coefficient K here has to be integer, because if I want this flux to be quantized, I can integrate this over the tree surface, and for this whole thing to be well defined, because Chern-Simon integrate on the tree surface is an integer, then this piece has to be integer too. Okay, I would gloss over this cohomology stuff, but for other things, if you like to receive more details, these two papers are pretty nice, and the Cordova talk in spring last year, and also like there's a review of how do you see this thing by relaxing the group axioms. And from a more mathematical perspective, which is surprisingly readable in this paper by Bass and Water in 2010. So I will skip this as well. If you want to see like how do you see that, how do you get the two group from make the associativity by relaxing the associativity, then I can come back to this at the end, but it's not so important right now. Okay, so now, we kind of sort of know what is a two group. Let's try building hydrodynamic. So for the ideal level, then it is okay to look at hydrodynamic as an analytic continuations of a theory that you define on the cylinder with a side S1. So you can try to write down the partition function, which is a functions of parameters in this theory. So for the theory with the global U1 symmetry, you have a background U1 gauge field. And so you say that, okay, my partition function can only depend on not so many parameters. It can depend on the size of the thermal cycle, and it can depend on the Wilson loop that wrap around this thermal cycle. And this would be it. So you do that in this following ways. And you put it in the curve space, and so that things couple to the background field properly, and you vary it, and you will find that the current is in the following form, which is the most general form that you can write. But by putting it in this form, it automatically gives you like the first law of thermodynamic and the extensivity condition. You can get the same constraint from like cooking up some entropy current and demand that it doesn't produce, that its divergence is 0, which is what you expected from from ideal fluid that is anticipated. Now you can try to kind of get the same information from holography as well. For example, let's take the bulk to be the usual Maxwell field, and let me write it in terms of like the boundary components and the radial component. Now what I can do is I say, okay, well, the boundary component at infinity would be just the boundary gauge field, and I also have the additional operators, which is the Wilson line connecting from the boundary to the horizon, or some horizon to some radius r. Now I can choose the radial gauge and move these objects to combine with the background field in the bulk with the gauge field in the bulk and combine into this object. So why am I doing this kind of thing? So we know that the partition function of the system, it has to be gauge invariant, like the gauge invariant in the bulk. So, and usually we just say that that this theory depends on the chemical potential, which is just a T component of the gauge field. So I used to wonder like why in the universe it depends on the gauge field alone. Like what about gauge invariance and all that? So, and this is actually why. So you can see that by choosing the radial gauge, you combine things in this way, and you can demand the regularity conditions of the time component at the horizon to be 0, and you left with the following residual gauge transformation, shifting this phi operator. And the only operator that is invariant at 0 derivative in this setup is mu, which is the AT at R to infinity. So this is basically like holographic argument of see like why at 0 derivative this theory can only depend on the chemical potential. If you break the residual gauge transformation completely in the bulk, like when you have holographic superconductor and all that, then you're allowed to have something else, like, and the hydrodynamic relation will change and into the superfluid one. Okay. I should mention that this is these kind of Wilson line is the operator that Nickel and Son and Dubovsky and Nicolis and Son used to construct effective action of the fluid, and you can generalize like this setup to patch a different space-time together to build Schwinger-Keldysh effective action. This was done in these two papers. Okay, so let's do let's try to build hydrodynamic for the one form fluid, to the fluid with one form global symmetry, basically the one with a constant number of strings. So here what you can do is, well, you have the system that is depends on the size of the thermal cycle, which is the temperature, and then you can try to imagine the analog of the Wilson line. But let's imagine we put a theory on a torus cross some manifold, and you can put you can wrap the two form field integrate it over the torus, and then you define like something like a Wilson surface. So once you do this, then the constitutive relation that you get can be written in the following way, where this rho B is the number of the string per unit area with some chemical potential mu, and this H is the vector where along the directions of the string, where it basically tells you where the string pointed along. So at the ideal level, this was like, I think it was the earlier one that I can find is the one, a book by Anil in '89. It's like a year before I was born. It's rehashed over and over, rehashed again in Aran and company when they talk about like a black hole story, and the classifications of dissipative terms. So it was done like quite recently by Shubring in 2014, and then by Sasho Gasanov, Diego Hoffman, and Nabil Iqbal. And effective action and all these things like follow quite shortly. I can, if you're really curious, like how is it related to the theory of magnetohydrodynamics, I can tell you about that, but it's not. If not, then I will skip this slide as well. I guess I would just skip this slide just for the sake of it. Okay, so now let's imagine, like, we tell you about like how to construct it from like a using sheet and all that. So what does it look like to deconstruct it from holography? So let's imagine the simplest one, where you have a bulk two-form gauge field, and the simplest action is written in this way. So, and there is some issues about the dictionary about the dictionary on the boundary of how to relate source and how to relate these thing at infinity to the source, but I will not talk about that. It's not so important right now. So you play pretty much the same game, right? You say that, okay, the B mu nu component at roughly r goes to infinity is the source, and you can make like some sort of object, like some gauge field, by integrating the B mu r along the r component. So you can try to make an invariant object by by wrapping this direction on the compact direction on the torus or some circle to make the Wilson sheet. But it's just like, imagine like this is some sheet that you integrate like this B mu r over, and it's stretched from the boundary to the horizon. You can try choosing the radial gauge as well. And now it will be moving things in this way, and you impose irregularity conditions on this object that left the following residual gauge transformation. Now you can build the only invariant object you can build out of this is therefore this object be 0 mu, which you can use it to define the chemical potential. So it turns out that this is something that people call a chemical shift symmetry. That this is what Glorioso and Son and Landry used to build effective action for the higher forms of it. So you can say that this is like a holographic derivation of this chemical shifting, if you're familiar with those. Okay, so now let's go. We kind of like have all the background material at play. So let's see how to apply this for the two group. So previously, we have the chemical potential, which is the Wilson sheet that you integrate the two-form gauge field over some torus or some two-dimensional objects. But there is a problem. It used to be this object is perfectly invariant under the usual ordinary one-form transformation. But now, because like the two-group transformation has additional piece, then it's not quite invariant anymore, right? So the thing that you think would be chemical potential now is transformed like the anomalous condition function, where this last piece, it looks like the anomaly term, the phase ambiguity once you transform the partition function in the U1 with the U1 anomaly in 1+1D. So to allow the string density, you need to add some other stuff to make a good chemical potential. And there is a trick that people use to do that. I think the one closest related to this would be the one by Dubovsky, Liam Hui, and Nicolis. And there's generalization versions and stuff that get more explained better over the years. But there's a procedure that you can do. But it's a Wessel-Minot type term that looks like the following, where mu is the zero form chemical potential and A is the background U1 field. You will see how this actually pop out in holography in a bit. But the point I want to mention is that this generates a term that, by for this thing to be consistent, then it will generate a term in the T mu nu that looks like the following. So kappa is the structure constant, mu A is chemical potential, rho B is the magnetic flux density, and U is fluid velocity, and H is this direction along the magnetic flux line. You can try to do it in different ways. One way that we think this is quite convincing is that if you replace the identity of your theory by this relation, and then you try to play the game of entropy current, then you will find that the entropy current can actually decrease, where it's supposed to be 0 because we are looking in the ideal limit. The computation is essentially similar to the computation for anomalous fluid in 1+1 dimension. Okay, so there are new terms in the constitutive relation that related to these objects, to bunch of chemical potential and densities, and most importantly, like this two-group structure constant. All right, so let's see what does it mean. So firstly, the first new term here, like this term, it implies that there is an equilibrium, non-trivial equilibrium current that's popping out in this way. And this means that, let's say you have a theory of magnetic field line and with some density inside, and that there is a current flowing along the magnetic field line. So unlike the anomalous hydrodynamic in higher dimension, those terms usually appears at subleading order in the relative expansion. This one, it always appears at 0 order. And this is the current that you would see that would you can track the microscopic commutation and see that this is something that's coming from the fermion zero mode that I mentioned earlier in the string picture. You can also compute the new modes, and then like what kind of sound mode that these theory have, and then you can see that they're modified speed of sound, and the prominent one is a transverse sound. Like this is like the sound where you plug the magnetic field line on the direction perpendicular to the string, and it propagates along the string. It's like a string on the guitar. So previously, without the two-group structure, then it would be symmetric between left and right. There's a wave moving left or a wave moving right at the same speed. But now with the two-group structure constant, it's not anymore. Also, if you do the longitudinal perturbation along the string, then you will find that there is a chiral sound mode. So basically a sound mode that travels only in one direction. So in basically this relation, instead of like plus and minus here.
Sorry, before you continue, can you comment on these fermion zero modes? I mean, because we have an effective theory, so it has nothing. I mean, you don't know whether you have fermion or anything.
Right. Okay. So you can do the free theory computation for the system, a QED-like system that we know that it has a two-group global symmetry, and compute the
Hey Nick, I think we lost you.
Did I just unmute myself?
Yeah, you muted one of your user, so you have to start again answering the question. But I think we hear you now. So.
Hello?
Yes, it's okay.
Yeah, we hear you now. Yeah.
Yeah.
Yeah. All right. So that's but the slide is still moving or not?
Now it's fixing. What does this mean?
Dear. Okay, then let me let me close that window over there. So basically, the other me is disconnected, right?
Well, it's still appears. I can still see it, so I don't know.
Okay, apparently Zoom, my Zoom on my iPad is frozen.
I see.
Let's see. What do we do next?
Yeah, either you, if you can, either restart the other one or
I'm restarting the other one right now.
or move the slides to this one. This one seems to be working well.
You could.
Recording in progress.
Oh God. I think this is not working. I'm just gonna share the screen from this one, but you guys have to shout because I will not see who will be. I cannot see who will be talking to me. It's make me nervous. I don't know who do I talk to. All right. Okay, let's share the screen again. And there we are. So do you see the slide?
Yeah. Okay.
Guys, is everything okay?
It seems so. Yeah. Now you can. Yeah. The slides are moving. So yes.
All right. Okay.
There we are.
All right. Okay. Great. Okay. Good. Then you know now we can finally that was previously. I don't know why did I stop. Like it's
You stopped. You were answering the question whether there were fermions at zero modes or not. Maybe Mihailo can ask the question again. I don't know, in case you don't remember.
Yeah, so I was just wondering, so in which context is that? Because in principle, you have an effective theory and you could have any matter content, so.
That's right. So again, like I think what I mentioned earlier, I'm not sure how much of it was a transfer, but you can try to do the computation for the current in finite temperature in the QED example that I just mentioned, and then you can see that there is the thing that correspond to these currents and to this current here and this mode will be are the fermion zero modes. But what the derivation so far is not assuming any of those. But you know, if you know your microscopic theory, you can track it down.
Okay, clear. Thanks.
All right. Okay, so now you can try to see like how do we get these things from holographic dual, where you know in the previous example it looks like it's a trivial thing, like why would I do this thing? But it's actually quite non-trivial for the two group, and it gives us the answer that we know from like that previous construction. So let's do the simplest holographic dual. You have like let's say for 5 dimension for the sake of it, but you know you can do it you can change like these d to the 5 to any d as long as you have non-trivial Simon terms. And this is the term that was proposed by these people. It essentially, these are the invariant 3-form field strength that I just mentioned before, that just dB square is not enough because the weird transformation you have to compensate by Chern-Simon terms. So you just add this term to the game, and you know, you have the 2-group gauge theory in the bulk, and it's corresponding to a system with 2-group global symmetry. Now you can try to play the same game. You have a gauge field equal to the bulk gauge field along the spatial direction equal to the boundary gauge field, and the same as for the 2-form one. You can have like a Wilson line attaching going from the bulk to the boundary. Now, and the other object, which is like the surface operator, this looks a bit weird. but you see why it looks in this way in a bit. So it is basically amount to the way that you do the radial gauge. So what you can do, just to, if we cannot remember that the two group transformation is, oh my God, it's quite far away, isn't it? It's this thing, right? This one. Okay. Oh, I actually, yeah. Why would I need to do that? It is already here. Yes. So there's this two group transformation, and I want to pick the gauge. Now, the order of doing this thing is actually quite important, because I can try to pick the radial gauge by tuning use the one form transformation lambda here to pick the gauge first. But if I were to do the zero form transformation to pick the other radial gauge here, it go out of that radial gauge by this extra piece of transformation. So you have to do the zero form gauge transformation first, like take A to D lambda, to make the big A, capital A into the curly A in this form, and then you do like the other U1 gauge, the one form U1 gauge transformation in the bulk, and to pick the gauge for the B field. So you do that, and this curly phi here that does the job of taking a radial gauge is written in this way. So now after regularity condition, say that the time component of A is 0 and the BTR component is 0, there is still a residual gauge transformation, which is this form. So C is the scalar field, similar to the residual gauge transformation in the Maxwell case, and the big C is the one in the Klaproth case. Now it combined this form. So the combinations that is invariant under residual gauge transformations, there are not so many, and in fact there are only two, which are these two, and these are the chemical potentials of the zero form of the usual density, and this guy would be the chemical potential for the string with the zero mode inside. Okay, and what the prediction that I just mentioned, you can also see in holographic duo. You can look at the equation of motion for this system, and let's say we look at the probe limit where the chemical potential is much smaller than the temperature, so that the background remains as Schwarzschild. And you can solve this equation, and you will find that, well, if AT is non-zero, then AZ has a non-trivial profile in the bulk. So this means that there is a current along the Z direction whenever I turn on the finite density for the string and the chemical potential for for the ordinary Maxwell field. Similarly, you can also compute the quasi-normal mode. I claim that there is a chiral mode in the bulk, in the hydrodynamic prediction along the direction of the string, and that it is related to a zero mode if you know the macroscopic theory. You can also do that, compute the quasi-normal mode in the bulk, and then this is what you find. So the dashed line is the hydrodynamic prediction coming from this formula, where chi AA is a susceptibility, and then the dot line are the numerical result. So you can see that at low energy, this is a pretty good agreement. So I should mention that. So what are we doing here? You can also ask like why, well, how is this really different from the anomalous fluid? Or let's say if I have anomaly fluid with mixed anomaly and I add the Maxwell field, like how would it differ? So usually, as I mentioned earlier, the anomaly transport usually occur at n-1 order in derivative expansion for the 2n dimensional field theory. Now two group, you can obtain it from gauging the anomalous theory, but it doesn't have to. There are other mechanism that it can came from, and the new transport into two group always happen at zero order. So also in the anomalous fluid case, the magnetic field is usually it treat as a source. It's not dynamical, and it come in at the first order in derivative. In this case, the magnetic field or the string density is just, it's a density, it's a zero derivative object, and you can allow it to be dynamical. The number of sound are different. So let's say in 4 dimensions, the the number of sound for the anomalous fluid does not change, because the anomaly piece enter at first derivative level only. But in this case, it does change. So it changed in two ways. Firstly, you have you make a magnetic field, you make the magnetic field dynamical. So you have a string which you can shake along the magnetic field line, and this is like the transverse sound in the in plasma. And also you have this additional chiral sound mode that we see over here. For some equation of state, you can gauge the anomalous fluid coupled with a Maxwell field that we saw earlier in the first few slides. It comes at the cost of gradient expansion. In this case, you assume you assume no splitting of the partition function, and you don't assume and the gradient expansion is still fine. So what actually end up happening here is that, so we try to expand hydrodynamic framework to, at least one of these things called higher structure. It's something that is not quite a group, but it is described the symmetry of a point of view theory. So we can also try to get more ambitious and say, okay, well, can you do it? Can you do hydrodynamics with any structure that is not necessarily a group, if it exists? And then we have a phenomenon, like a new phenomena, which is similar to the anomaly-induced transport. One can also ask, like, okay, in this case, I only look at a system where I gauge one of the U1 of a system with a mixed anomaly, and it's actually only one of mixed anomaly. There are two of them that is possible. We don't know how to do it with the other one. And also, like, the other thing, which is quite probably like a more philosophical rather than just application, is that, like, we were wondering whether can we bypass the gauging procedure. Instead of like having one symmetry and you gauge the symmetry and then you arrive at something else, can we just bypass that process and just say, okay, well, what you have after that is this global symmetry. It can be categories, it can be higher group, it can be a group, doesn't matter. But we have a hydrodynamic version for doing those things. And that is that is it. That is pretty much all I have to say. Am I doing okay with time? Yeah, I guess I'm still fine. Thank you so much.
Thank you, Nick. Very nice. You did very well with time, so we have time for questions.
So the quasi-normal mode that you showed us, that's of the gauge field itself. Okay, so so now when you couple it to metric fluctuations, is that much harder to do? I mean, is the calculation much more involved, or?
Yes, it's much more involved. So firstly, we're only working in the probe limit, where we don't have to back react the background. If we were to do that, then even with just the string without magnetic field, you get the magnetized backplane solution. It's quite easy to get it numerically, but the system is anisotropic because you have a preferred direction along the direction of the string. So
there's basically so there's no chance of I see.
Yeah, so the background has to be that numerical if you were to do it consistently.
Mm-hmm.
If I saw Giorgio raise a hand.
Well, I'm next. Did you finish answering the previous question? Yeah. Okay. I guess my direct question is there a physical system where you think this approach is phenomenologically useful? You mentioned magnetohydrodynamics, and in the reply to my previous question. The thing is that experimentally, magnetohydrodynamics is very highly unstable, right? You have plasma instabilities.
Mm-hmm.
And from an effective theory point of view, this can sort of be rationalized by the fact that scale separation in magnetohydrodynamics, any kind of scale separation, doesn't really work because you have a you have a mixture between a completely coherent zero entropy system, which is the magnetic field, and a nearly thermalized system, which is the fluid interacting with the magnetic field.
Mhm.
And so scale separation becomes problematic, and instabilities can be kind of understood this way. You mentioned field lines in a superconductor. You mentioned magnetic field lines in a superconductor.
Mhm.
So would a turbulent superconductor, would a turbulent superfluid or something like this be an example of where this might describe a real physical system? Sorry, superconductor. Yeah.
Yeah. Okay. So I suppose we were talking about this example, right? So okay. So what the system that this could apply, like the simplest one, is it's a essentially QED in 4 dimension with one mixed anomaly. So you can if you have just like one massless fermion, then they're actually, okay. So for U1 anomaly, U1 cross U1 anomaly, there's 4 anomaly terms that you can possibly write down. For if you have one massless Dirac fermion in 4 dimension, I think you have one of them or 1 or 2 of them, but not this one, not the one that I'm writing here. So this one you can make by engineering like maybe 2 species of fermion, assigning the charge properly to kill other anomaly, and you're left with this one. So it's kind of artificial. I don't know whether you can like precisely have, or any other system where you can have this term.
Would QCD with massless, if you consider Wilson loops in QCD with massless quarks, would it approach something similar or not?
Yes, this is very good. Yes, you can have those systems, but it's not going to look quite like what I have. So in those cases, the one form symmetry, like the one that is a string, that count the string, it's not the U1, but it's a CN global symmetry, which is a center SUN of the SUN view. Or you can have a case where you have a mixed anomaly between like a flavor and a CN global symmetry. I'm not sure how to write hydrodynamic for those things, but it might be possible. In this case, I'm only working at the U1. So in this case, yeah, maybe to answer your question honestly, I don't know whether this current version would be applicable to things useful that people in, let's say, like chiromate or hydrodynamic and these kind of things were doing. We do it because we can. What we would like for gauging different anomalies, but we don't know how to do that yet. The interesting QFT where you have like this higher group structure, it mostly involves the CN symmetry, which I guess we can try to break the U1 to the CN, but we don't know how to do that systematically yet.
Okay, thank you.
More questions? No more questions? Well, if there's no more questions, I will stop the recording and then ask for questions again. Let's see them. So, but then first, let me thank you again, Nick, for the talk. It was very nice. And also say that we'll see each other. We'll have another talk in a week by Nabil, who's here. So stay tuned. So now let me stop the recording.